Bubble column reactors are widely used in the petroleum and petrochemical process industries. In many applications, the bubble column reactors operate at elevated pressures. For example, in the Fischer-Tropsch synthesis, bubble column slurry reactors are used in industrial practice, and such reactors are operated at pressures of about 40 bars. In this presentation, I'll look at the influence of elevated pressures on flow regime transitions in bubble columns. The information I will present is based on publications from my research group. I'll list here a couple. So let's look at flow regime transitions in air-water bubble columns to start with. Let's first look at an air-water bubble column operating at ambient pressures of 1 atmosphere. We start with a glass column filled with water, and we sparge air through it at a velocity of 4 millimeters per second. And if we look at the flow regime, we see fairly uniform sized bubbles that rise through the column at a velocity of approximately 20 to 25 centimeters per second. This regime of operation is called the homogeneous flow regime. This is to be contrasted with a flow regime that occurs when we operate at higher gas velocity, say at 27 centimeters per second. We have the heterogeneous flow regime, in which we see large bubbles coexisting with small bubbles. The large bubbles may rise at a velocity of approximately 80 centimeters per second to 1 meter per second, significantly higher than the rise velocity of the small bubbles, which are approximately about 20 to 25 centimeters per second. So for atmospheric bubble columns, we have a homogeneous and heterogeneous flow regime, and from a practical point of view, it is important to know the transition from homogeneous to heterogeneous flow regimes. Let's examine the influence of pressure on flow regime transitions. Let us examine the influence of increased pressure on the flow regimes in a bubble column. The bubble column has a viewing port which is circular, and let us first examine a column that is operating at, say, 5.3 centimeters per second and at a pressure of 1 bar. We can see fairly uniform bubbles rising through the column. If we increase the pressure to 5 bars and look at the bubbles inside the column through the viewing port, we see that at elevated pressures, the bubbles are smaller in size and there are more of them. If we increase the pressure to 10 bars, we again see very small bubbles, significantly smaller than the bubbles that exist at atmospheric operations. So if we plot the gas holdup against the superficial gas velocity, we see there is a difference in the gas holdup at 1 bar and 5 bar operation and 10 bar operation here. So the gas holdup increases with increasing pressure, because the bubbles are smaller, and apparently the bubble rise velocity is also reduced, resulting in a larger gas holdup. We now examine the influence of elevated pressures on the bubble column hydrodynamics for an air-water system with a superficial gas velocity of 10 centimeters per second. Let's start with atmospheric operation, and if you watch carefully, you will see once in a while large bubbles passing through the viewing port. So we have the heterogeneous regime of operation at 1 atmosphere. If we increase the pressure to 5 bars, we see that the bubbles are much smaller and no large bubbles are detected. So we have a homogeneous bubbly flow at 5 bars. If we increase the pressure further to 10 bars, again we see a lot of small bubbles and no large bubbles are visible for the duration of the video recording. If we plot the gas velocity against the gas holdup for 1 bar operation, we have the red circles, and this is the operation at 5 bars, inverted blue triangles, and green pluses are the 10 bar operation. Importantly, we see that at a velocity of 10 centimeters per second, we have clearly heterogeneous flow regime for operation at 1 bar, but homogeneous flow regime at operation of 5 bars and 10 bars. So the regime transition from homogeneous to heterogeneous flow regime is delayed by increasing the system pressure. We now examine video recordings of the bubble hydrodynamics for a column operating at a superficial gas velocity of about 15 centimeters per second. We examine operations at 1 bar, 5 bars, and 10 bars. So let's start with atmospheric operation. We see at 15 centimeters per second, we have large bubbles coexisting with small bubbles, and we clearly have the heterogeneous flow regime. If we increase the pressure to 5 bars, we still see large bubbles going up, shooting through the column, coexisting with small bubbles. So heterogeneous flow regime persists at 5 bar operation. Let's increase the pressure to 10 bar. We see there are a lot more small bubbles as compared to atmospheric operation, but the large bubbles still persist. So we have heterogeneous flow regimes at 1 bar, 5 bars, and 10 bars. But if we observe the differences in the 3 video recordings, we see a lot more small bubbles are present with increasing system pressures. If you plot the gas holdup against gas velocity, we have 1 bar operation here, 5 bar operation here, and 10 bar operation here. So the superficial gas velocity of say about 15 centimeters per second, all 3 pressures at operating pressures, we have the heterogeneous flow regime. However, if the velocity is say 5 centimeters per second, they have only heterogeneous flow regime at 1 bar and homogeneous flow regime at 5 bars and 10 bars. So the important takeaways from these video recordings are that increasing system pressure delays the transition from homogeneous to heterogeneous flow regime. This slide summarizes the influence of increasing superficial gas velocity and increasing pressure on bubble column hydrodynamics. At say atmospheric operations, increasing the superficial gas velocity leads to transition from homogeneous bubbly flow to heterogeneous flow regime. If we increase the pressure, we have more small bubbles and reduced amount of large bubbles, and these small bubbles are smaller in size than the bubbles at say atmospheric operation, and therefore their rise velocity is lower, resulting in higher gas holdups, as shown here. Comparison between 1 bar operation, 5 bar operation, and 10 bar operation. If we increase the pressure even further, we may delay the transition from homogeneous to heterogeneous flow regime, and when the pressure is high enough, no large bubbles are observed, and we have homogeneous flow regime. Only at very elevated superficial gas velocities we have the heterogeneous regime of operation. So increasing pressure leads to a delay in flow regime transitions. The small bubbles rise less fast than at atmospheric operation, and the gas holdup is increased.